Okay, so we are ready here. Can you check your mic?
Yes, hello.
Oh,
Yeah,
well,
that's kind of loud.
Excellent.
But
That
yeah,
was a roar.
we can hear it.
Okay, right. So next up, we're going to have Philipp Krenn from Austria, Vienna,
Yes.
and he's a developer advocate for Elastic, if I'm not
Yes.
wrong. Okay, and he's going to take us beyond CAP Theorem. I understand, right?
Beyond CAP Theorem, and like we have our own theory around like limitations of what you have. So this talk is mainly about kind of limitations that you have in your data store.
Excellent. All right. So
let's see where we can take this. It's the first time I'm doing this talk, so let's see how it goes. So thanks for the introduction already. Yeah, I work for Elastic, the company behind Elasticsearch, Logstash, Kibana, Beats. You might either use us for full text search, or we're also very kind of popular in the logging and monitoring space. And yeah, I run around conferences, do trainings, talk a lot of all the good stuff that we do. So let's see where we can take this today. I also run, since I'm in Vienna, some meetups. So I run one on databases and one on academic papers. And this talk is a bit of the combination of like some theory and some practice around databases. So it's kind of like potpourri or best of what you can do in those areas. So a common question you get is like, what is the perfect data store? What should I use? What is the one data store that people are using? And is anybody a consultant here? Nobody dares to admit. Okay, because the answer of consultant is normally it depends. And that after that depends comes a big bill normally. That is kind of like the consulting approach. But I must admit that we have kind of the same approach, that it really depends on what you want to do with your data store. That dictates of what you ideally use. And you really need to pick your trade-offs. And this talk is mainly about the trade-offs that you need to pick in your talk. So there is no magic, even though some people pretend there is, and it looks like their system looks something like this, but there is really not. It's just about the right trade-offs that you want to pick. So I guess most of you are familiar with the CAP theorem. Who is familiar with the CAP theorem? Okay, that's new. Not everybody. I have it in my slides anyway. I would have shown you anyway, even if everybody had raised their hand. So the CAP theorem, it was based on this paper. So the theory came up in, I think, 2000, and in 2002, they wrote this paper. And it says about web services, but this is really about every distributed system, and very much includes anything that is a data store. So you have 3 attributes, and generally you want to have all of them, but you can only have 2. And what that says is like, the first attribute you have there is consistency. So basically, even though you have a distributed system, you want to have this, it should look like it was a single system, and all the operations were executed one after the other, in the same order for everything. That is the consistency part. So the consistency part is like the timely order of all the events that you have in your system. The next one is availability. Like as soon as a service or a node in your system is reachable, it should respond to all requests. It just cannot say like, oh, I'm not sure what the state is of the cluster right now, I'm not answering your requests. Availability basically means like as soon as as long as the node can do some work, it should be doing that work. And the final attribute is partition tolerance, which is kind of a given in a distributed system, which basically says you can lose arbitrary messages in your system. So basically any message can get lost on its way in the network, and your system should still be able to operate. And what the CAP theorem basically proves or shows is that out of these 3 attributes that you want to have, you can at most have 2. And what that basically looks like is you have the 3 attributes, and you can only be in these little colored areas. But there is no middle where you have all the attributes combined. And if you build your system badly, by the way, you could just be in the circle of one of them. Or if you build a very bad system, you could be outside of all the circles as well, where it's just like random stuff happens. So it's not guaranteed that you will have even one of these attributes is not guaranteed if you implement it badly, or if you don't optimize for it. And then you can also explain that whole concept to your parents or to your kids. So if you have kids at home and you want to tell them a story tonight, you can explain them the CAP theorem as with Robinson Crusoe, if they know who know Robinson Crusoe is. So the idea is basically Robinson Crusoe is on his island, and he's kind of partitioned from the rest of the world. So the partitioning is a given in the distributed system. And then a ship comes by and they ask him a current question. And then he basically needs to decide, am I consistent or am I available? Because if he answers he's available, but maybe he's not consistent with the rest of the world, since he didn't kind of get the updates of what is happening in the world, since he's partitioned on his island. The other approach would be that he says like, oh, I'm consistent. I'm not really sure what is going on in the world, so I'm not answering. And that is generally the idea of the CAP theorem. And it's the paper is not very math heavy, it's pretty constructive. So the assumption in an IT system is basically you have a 3-node cluster and you have 2 nodes on one side and 1 node on the other. And the network in between is broken. And then you write to one side of the nodes, for example. And then you query the other side. And that other side basically can decide, am I consistent or am I available? And it's kind of obvious if you frame it like that you can only have 2 of these attributes, but not the third one. Because something has to give in that scenario. So that is the CAP theorem and the trade-off around the CAP theorem. Some systems avoid to break the CAP theorem, that is def null, because that kind of has all the attributes. But that doesn't make it a useful system to store data. You can do it, and you might beat the CAP theorem, but that's not really the point. So these trade-offs, yeah, you might find a way around them, but that's not the end goal. So we have our own thing. It's not called the CAP theorem, but we call it the FAB theory. We haven't written a fancy paper around it. That's why we only call it a theory. And we have also 3 attributes, and we say you can only pick 2. And the first one is fast. Fast basically means something happens in real time or near real time. It's basically a user sits there, does something, and waits for the result to come back. It's not like batch-oriented, where you go for a coffee or you let it run overnight. It's more or less real time. And a lot of systems should be like, it should be like milliseconds or a few seconds and not more. That is one of the attributes a lot of modern systems should have. The next one is accurate, that is kind of a weird one, because everybody assumes like their system should be accurate, right? You should have the exact result and not just an approximation. But that is another trade-off that you can do, the approximation. And then the final one is big. And I know there are a ton of definitions of what big actually means. And there are, for example, these 3 V's, like volume, you have a lot of data; variety, like your data is very varied, or like different fields are missing or are there; and velocity, like you have a very spiky load. I will stick to a very simple definition. It's basically something that cannot be run on a single computer. So everybody who tells you I'm running a big data demo on my laptop is telling you some crap. Because there's kind of the definition of that big data is not on a single machine. Yeah, and people have continued that V ID. So I've seen that the post with the most V's is 42. And that's pretty much like, I think they just went through the dictionary and took out every V word that they could basically fit in there. And there is stuff like vulnerability and voodoo in there now as well. So yeah, you need to use all the V's at some point. But generally, I don't really like the term big data. It's pretty much like this. It's kind of like the very overhyped marketing term, and everybody says we're doing big data, and nobody really knows what it means, and it lost any meaning, but everybody is throwing around big data. But let's assume you have some large data set. So it doesn't fit on a single computer. And fast is kind of easy to understand as well. It's like, it will respond fast enough so I can wait for it. What is this approximate? I want to kind of dive into that approximate, because we, with Elasticsearch, we have a system that can do this approximation approach for some queries, and you can tune it. It's kind of like you can tune then how much performance do you want to spend, and how accurate do you want your results to be. So it's kind of a knob or a tweak that you can tune. So generally, the idea is we have data stored in Elasticsearch, and the scaling concept we have is a shard, which is kind of like, you have a so-called index, which is just of like data that belongs together, and you can split that up into any number of shards that you want to have. And each one of these shards can then reside on a different node. So this is the scaling out system that we're using. A shard can be, multiple shards can be on the same node. Like I, in my demo, just have everything on a single node, and all the shards are on the same node. But you could totally spread those out over multiple nodes. Does anybody know where the term shard comes from? Because it's kind of very common to split up data. Anybody remembers this? Ultima Online, long time ago. this, at least the story I know, is that they came up with the term shard, and that's why the sharding in databases or in any system is called sharding. Because there was the wizard, and he put the essence of the game in, or of a world, in a crystal. And at the end, that crystal was shattered, and it was split into different crystal shards. And that, like every of these shards, contains a part of the world. So every shard in a database system contains a part of the data that makes up the entire world or data amount that you have. So that is where the term is generally coming from. Okay, if you want to replicate this, everybody needs to use Docker, and I think everybody needs to show Docker in the slide, so I've done that. Though I think that would be the right Docker logo. Should look something like this. Anyway, if you want to use this on Docker, this is the way to do it. I'm using Kibana since it's easier to interact with it, and then you have Elasticsearch to store the data. But that's all easy. Docker Compose up. It will download half the internet, and then you're up and running. So this is all simple. We have two examples of things where we have kind of a trade-off between performance and correctness. And the first one is the terms aggregation. And I'm using Star Wars quotes now. So in the very first Star Wars film, which I think is now number 4, since they had the prequel and whatever, these are some of the well-known terms that appear in that film and how many times they appear. So you can see Luke was the most common word, kind of like relevant to the Star Wars ecosystem in a movie, which appeared 64 times. And then R2, which appeared 31 times, etc. So I just picked, I don't know how many those are, 18 or something like that, terms from the list. Somebody else did the counting. I didn't watch the movie to count. I might just using those. I'm creating an index with 5 shards, so it's split up into these 5 pieces. So I could spread that out over 5 nodes. Though in my example, I'm just having everything on my 1 node, but you could totally spread it out over your 5 nodes. Or if you have more nodes, you would need more shards to spread it out over those as well. So what I enter is basically I'm throwing in all these documents. So I have Luke 64 times and the other documents the same amount of time. You can then visualize the whole thing, so you can see Luke is the most common one, and then C3PO and whatever all the other terms are. And you can see, yes, these are the terms we have stored those. You can even search those. And just to show you that I'm not cheating, we can, of course, do that live. So yeah, this is the visualization of the terms. We have stored those. I have already inserted the data, so like every good cook, I have prepared something, basically. Now we can run the query, and we can see if we're searching for Luke, it is being found 64 times. This is the right amount of Lukes we have or should have stored in our system. And now I run this query here, which might be slightly small to read. I hope this is readable for everybody. So you can see I'm running an aggregation, and I basically want to see the most common term, and I aggregate on that field where I've stored it, and I want the one most common term. So basically what I'm expecting is that it will say Luke is the most common term or word, and it will appear how many times? 64. If I run that, what happens, however, is it tells me, yeah, Luke is the most common one, but it appears 56 times, which is, yeah, it's kind of like the most common term is kind of correct, but the actual count is wrong. And yeah, Luke probably wouldn't disagree, and he would say something like, it's impossible. Why? What happened in our system? So I kind of cheated here, or I kind of prepared the data in the right way to have this anomaly. So we have this, at the very end of every line, we have this routing. So basically I say the first document goes, uses the routing key 0, and then 1, and up to 9. But after 9, I route all of those keys to the same number. And basically that determines into which shard that data is being stored. So I'm kind of skewing that data. The first 10 entries are evenly distributed by chance, basically, over all my shards. But the other ones are all going to the same shards, and that will be relevant to kind of like skew that counting. So because how we basically route that is we take that routing value, hash it, and then count it modulo the number of the primary shards. So modulo 5, and that will determine like this will be in this one shard or in this other shard. And if you check out where your data is, you can also already see like these are my 5 primary shards, and you can see the docs. Like already the docs are not very evenly distributed. Like one shard has 26, and the next one has 71. So the data is not that evenly distributed. But that was kind of like because I designed it to be like that, to make it more obvious in our example. And what we're getting is basically every shard is always operating independently. So basically we are running this aggregation on every single shard, and every single shard is calculating its own sub-result. And then we're combining all the sub-results to the overall result. And what every one of these shards is doing basically, we're using an implicit shard size, which basically says size I used in my example was 1, because I wanted the top 1 result. So every one of my shards is calculating the top, according to that formula, the top n results it has in there, which comes down to 11, because it should be rounded down. Because we have the size we want the top 1 result is 1 times 1.5 will be rounded to 1 plus 10 will be 11. If you, for example, wanted the top 5 results, you would have 7 plus 10, 17. So this is like, and every single of my shards is giving me the top 11 results now it has. But since I've skewed that, like some will kind of like have specific values higher than others. So yeah, we've just done that. 11 shards or 11 results per shard. To aggregate my total result, how many results do I need to calculate or aggregate overall? 55, I had 5 shards, so every shard is giving me 11, the top 11 hits it had. So we are aggregating those 55 to the overall top 1 term in the end. And our result already has, that was kind of like hard to see before, it tells us there is an upper error bound and a doc count. Because basically it knows I'm only giving you the top 11 results I have, but there are more. So I could miss other results, and that upper bound is basically like the lowest value. So for example, if the 11th result on your shard has the value 2, that one shard can contribute a kind of error of up to 2 for the overall result, because it could miss some value with up to 2 from that shard. So it basically tells me overall your results could be off by 10, and we have kind of like missed 232 documents. Those are all the non-Luke documents basically that we don't have in our result now. What you can even do is you can say, show me not kind of the overall error, but the error for one specific term. Because if we have Luke in our result set, it's already there, and I'm not adding any error for that in that case. So you can add that, and it would then tell you, yes, I found Luke 56 times, which is kind of close enough. That might be off by, or that might miss up to 9 results. So that would then be 65, which that would be 1 too many, but kind of we've made a kind of nearly worst case scenario that our result is kind of a bit off. But you can fix this, because you can set that shard size explicitly, and what I'm telling it now is basically every single shard should not give me 11, but 20 results. And since we only have 18 documents, this will include all of them. So I'm getting the top 20 results per shard. Overall, 20 times 5, now I need to aggregate 100 instead of 55. But if I run that, then it will give me the correct result. And I don't have any error rate here anymore. We have a very similar thing when you do full text search, which is also shard-based. So if I search for Luke, we always have this relevancy here. This is this underscore score field. And what is kind of curious, all the documents contain Luke, but some have like a relevancy of 3.199, and this one has 3.2, which kind of should be the same everywhere. But we're also optimizing for full text search a bit here. Yeah, give me 3 more minutes to dive into what is going on here. So, what we're doing behind the scenes is called kind of the full text search algorithm we're using is TF-IDF, term frequency inverse document frequency. And what that, I mean, we've kind of slightly optimized that now, but what that basically says or it consists of 3 things. The first thing is the so-called term frequency. When we're searching for something, if I'm searching for Luke, a document that contains Luke more times or multiple times is more relevant than a document that contains Luke just once. So basically, if you're searching for Luke and one document contains Luke 3 times, that's more relevant than if you contain Luke just once. That's kind of easy. Curve looks something like this. So you can see if a document appears 5 times, it's more relevant than if it just appears once. And with the new algorithm, we basically assume if it's 20 times, it doesn't make much difference anymore. It's just the same. The other thing is this is kind of dampened if a term is very common. So we know over all the documents we have in that index, how common is that one term overall. And that basically assumes the less common it is, so these are the number of occurrences. If a document or a specific term appears like 50 times, it is much more relevant than a term that only appears, or a term that appears hundreds of times. The problem is this calculation, how common is the term overall, is done on a per shard level and not globally again. And the final thing that is also in there but doesn't make much difference for this one is a shorter field is more relevant than a longer field. But all of that doesn't really matter because we have had like 64 documents with Luke and they only contained Luke. So the term frequency is the same because every document contains Luke once. The field length norm is the same because all of the documents just contain a single term. So that's what we have. The inverse document frequency is what makes that kind of very minor difference in our search result. And how we are doing this is basically we're going to all the shards and say we are searching for Luke. Give me your top results for Luke. And since by default we're searching for 10 documents, the 10 best documents overall, every shard would give you the top or its own top 10 results. And say like, hey, I have these documents and these scores for these documents. And then there would be a coordinating node which would take the top 10 results from every single node and see, okay, you have this score, and say, okay, overall, out of these 50, since it's 5 times 10, out of these 50, these are the 10 best documents overall. And then it would actually go to the nodes and say, and now fetch me that actual result. So in the first step, we're just calculating how relevant it is. And in the second one, we're actually fetching the document. What we're missing here is that this inverse document frequency, how common is the term over all my documents, is again off. Because Luke in one shard probably is like 40 times. Or actually, no. Since we have said like after 10 it's skewed, so 9 will be kind of evenly distributed of the Lukes, but 55, the first one and all the other ones, are on the same shard. So there the inverse document frequency is just off because on that one shard it assumes Luke appears lots of times, whereas on the other shards Luke appears only once or twice. And that's why that is off. And we can add optionally another step here, which is called DFS, Distributed Frequency Search, where we add another step at first, where we basically say this inverse document frequency will be calculated overall over all my shards, so that you know how common Luke is over all of them. And then the result will be the same, because if we search for Luke, you can see we have added this DFS at the end. Then all of them are 1.53 blah 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 whatever ending in 17. So here the score is now all the same, and you can also see the value of the score is generally lower because we have more Lukes in our overall system now. So that's what is making Luke kind of less relevant, because I think before it was 2.9 something or 3 the score. This is because now the document frequency is kind of like evened out over all my shards. So that was kind of easy. You can kind of brush it off. People often ask then like, okay, DFS sounds awesome. How much performance does it cost? And that is my favorite comic for all performance-related questions, because it really depends on what you have. So if you have a slow network, it will be totally dependent on your network, because you will have one more hop. If you have very slow disks, since we need to fetch data from the disk, it might be the disk that is adding more overhead. Obviously, DFS will be more costly, but it will totally depend on like how much data do you have, how fast is your network, how do your queries look like in general. So there is no easy way to say it's X% or X milliseconds. It really depends. But you generally don't need it, because normally you have a lot of documents, and if you have a lot of documents, it will even out over all the shards. And normally your documents will also be pretty evenly distributed amongst all the shards. So you don't need to worry about that much. There are only specific situations, especially when your data is kind of skewed, like in my example, then this will make a difference. And the other workaround is if you say, like, I don't want to be big, I want to have like the other attributes, you can just use a single shard, because then you don't have all these problems. Simon says it's kind of an internal joke because the tech lead of Elasticsearch is called Simon, and he always says use a single shard until it blows up, and then figure out what is the right shard size that you need, because multiple shards just add overhead if you don't need them. So only use as many shards as you need, and you can totally skip some of these problems. So just to show you what I'm doing here is I'm basically taking my Star Wars index that we had with the 5 shards, I'm shrinking it into a Star Wars single whatever index, which consists of a single shard. So basically instead of 5 shards, I have only 1 shard now. And when I run my queries now, you can see I don't need that DFS step because it's only a single shard. All the IDF values are already the same. And if you run the aggregation, now I don't need to set any source size. If I run the aggregation, it will also give me the right result. This doesn't mean, or yeah, now you could say this was kind of cheap. And you can totally do that if you don't need more shards, just don't do that. But that's kind of the point of that FAB theory, that if you need big data, you need to make that trade-off. But if you don't need that big data, make the big kind of trade-off. But if you need the big, you will need to make the trade-off, should it be accurate or not? And how fast should it be? Because you will add more overhead if you do it differently. So to conclude, it's kind of all about the trade-offs. Because you cannot have all the attributes at once. It will really depend on how you, or what you want to, or what is the goal of your thing. Yeah, we started off with the CAP theorem, and I tried to introduce the FAB theory that we have. Yeah, as I said, it's not a full paper, and it's kind of not proven, but we always say it's kind of like by intuition, we believe in the FAB theory, and probably you can see it in your systems as well. With that, I'm pretty much done. I think we're we're doing okay in time, I guess. If you want to grab stickers, I have a bunch of very bright colored whatever stickers over there. Take some. Do we have any questions? Yes. I think the microphone is right next to you. Oh, and by the way, before you all run off, I normally take a picture with you so I can prove to my colleagues that I've been working today. Because they don't know where I am normally. And so they only see my pictures when I say, hey, I did a conference. Smile, everybody. Okay, question.
Great talk, thanks.
Thank you.
So you mentioned it's all about trade-offs, right? And typically, right? And historically, the way I always known Elasticsearch was, it was designed to do search. So I have various things there which help with search. It seems to me that more recently, you are targeting other use cases as well. There is a bit of analytics there, and so on, right? So I was wondering if you could maybe give us a quick, very high-level picture of what are your, let's say, major advantages? Let's say you're competing with OLAP, right? What tools are you competing really with OLAP? Like, why do you see yourself as going to that space at all? Things like that, right? So essentially, what I'm saying is, given that historically you have the search use case and you're expanding to more, could you perhaps give us 1 or 2 sentences on what is your advantages, let's say, over other tools in other use cases?
Right, that's a great question because it's kind of confusing for lots of people because we started off as search, and then sometimes there's a question like, are we abandoning search now? Which is not the case. Like we always say, all of the other things that we're adding are also search problems. For example, after search, so by the way, if you're searching Wikipedia, GitHub, Stack Overflow, behind the search box, always Elasticsearch is doing the search. So that is kind of like very common for search use cases. Then we added the logs. Like initially it was called the Elk stack, now we call it the Elastic stack. Because we always say storing the logs is not what you want. You want is kind of like you want to find the logs. Like you say, I have this error, or what are my errors? So you want to find the stuff. The storing is kind of like just a side effect that you're not interested in. And we're trying to kind of like broadened out into other areas. So we, in version 5, we got very good with numbers, for example, or we improved a lot that numbers. For example, metrics. We can do metrics very efficiently, which can be either computer metrics, but it can also be business metrics. And we have kind of a bit more of a holistic approach because we have Elasticsearch is there to store the data. And then we have Logstash and Beats to get the data, and Kibana is there to visualize it. It's kind of like this package. And basically what our goal is we want to be more of a data platform. We don't really want to be the solution for problem X, but we kind of want to be a data platform that you can then adjust to different things. And we see a lot of value that you kind of like have one established tool, and you can do the search on your website, you can do the logs from your application, you can see the metrics, what is going on, but your business can also collect all the information like how are our sales being affected by the performance or the outages of our website. That you don't have like all these little islands and then you need to search like what business unit is, some business unit is doing this and some business unit is doing this, but you don't really have that big picture. Everybody will obviously have their own dashboard, kind of like about their key metrics, but you still want to be able to kind of like see what are the others doing and how is one department influencing another department. And that is kind of like the idea of where we want to go and want to push that. I hope that answers the question. Okay, you're welcome.
Cool. Any other questions?
Another question.
I have a kind of off-topic question. Why were the mappings deleted from Elasticsearch?
Types.
Yeah, mapping, like in the 6th version reduced to only 1 and in 7 completely deleted.
Multiple types per index, yes. So that the others don't get completely confused of what we're talking about here. Where's my search query? When I'm searching here, I have an index that is kind of like all the things that belong together, and then we used to have this type here. It's still there, it just will be removed in the future, because initially, we assumed everybody knows relational databases. So we said the index is like the database, and the type is like the table. And that was a really bad comparison, but that was kind of the initial idea of why we did that. The problem is, it was always a lie, because Lucene, which is storing the data on disk and is kind of like behind the scenes doing the actual work, doesn't have the concept of that type. And those multiple types were always confusing and kind of like actively harming things. And we're now doing a multi-year kind of cleanup of that. So starting in 6.0, you cannot create indices with multiple types. You can still keep using an index from 5 with multiple types that will keep working. But the type, you can, unless you change it in the configuration, you can only create a single type per index going forward in 6. In 7, the type will be optional in the API. So you can, in 7, you can change that. And that underscore doc, that will be the type that will make it optional. So if you create anything today, use underscore doc. Unfortunately, we only added underscore doc or allowed that in 6.2. And initially we recommended doc without the underscore. That was kind of a mistake. We're sorry. That was in 6.0 and 6.1. It was just doc, but that's not going to help you with the migration. Please use underscore doc because that will be optional in 7, and in 8 everything about types will be gone. And in 7 you will also not be able to create multiple types anymore, not even with a configuration flag anymore. And kind of the downsides were that since Lucene didn't know about this differentiation of the type, you would have various problems. One was you use multiple types and you would assume the fields would be independent. But that's not the case, since this is kind of like the type is just like an additional field we add. The fields were never independent. Assume you had a flag which says disabled for a user, for example, or something. And in one type, disabled is a Boolean flag, like user is disabled or user is not disabled. And then you think in another type, I will make the disabled, it's not a flag, but it's a timestamp. Like if it's set that user is disabled. But that doesn't work because it needs to be the same data type. And that would be something that is very confusing for people because it looks independent, but it really is not. Or even also if you're searching, like the inverse document frequency that I've shown, that will be used across types. So the inverse document frequency will be just the same across all the types. And that was also very confusing and would sometimes show bad results because people didn't expect that. They would expect that types are independent. It's like tables in the relational world, which are independent, but they're not. So that's why we're cleaning this up. Like the core team has had this wish for a long time to do that. And now finally they kind of took the step. But we're trying to make it as painless or pain-free as possible, since it's kind of like multiple iterations. There is not a big breaking change in one version, but it's kind of like you always have within one version, you have like, you can do one migration step. It will take us approximately 3 years or so to really get rid of it. So we are not trying to make it too hard, but it's like in the long run, it will be kind of a good improvement that needs to be there. I hope that answers. Yeah. Cool.
Anything else? No, I don't see anything. Okay, so thank you very much.
My pleasure.
Philipp.
Find me afterwards if you have any questions. I'm happy to answer anything that I know. Let's see.